Hello, today we're continuing in our A-level physics revision series looking at internal resistance. So far we've looked at the simplest form of Ohm's law, where we take a battery, we put it in a circuit with a resistance, and we say that a current flows, we call it the conventional current, flowing from plus, this is the plus side of the battery, this is the minus side of the battery. The conventional current flows from plus to minus, and we say that according to Ohm's law, V, which is the voltage of the battery, is equal to I, the current, times R, the resistance. That's famous Ohm's law. Of course, we know that in fact no such conventional current does flow. In fact, electrons flow from the negative side of the battery and they are attracted to the positive side because electrons have a negative charge. And unlike charges, attract, so a negative charge is attracted to the positive side of the battery. The reason that we talk about the conventional current flowing in this direction is that long before people understood what electricity was, or what even an electron was, they assumed that whatever was flowing must flow from plus to minus, and we maintain that fiction to the current day. But we actually know that, of course, the flow of electricity is really the flow of electrons. But that's by the by. Now, we've made an assumption in this diagram. Firstly, we've assumed that the wire, which connects the battery to the resistance, has no resistance, because we're not accounting for any resistance in the wire. And for all practical purposes, that's probably right, because we've probably used a copper wire, which has a very, very low resistance. It's not having any real impact on the circuit. All of the real resistance in the circuit is in the resistor here. So no great harm done by assuming that there's no resistance associated with the wire that is connecting the battery to the resistance. But we've also made another assumption, and that assumption is that there is no resistance in the battery itself, and that is usually wrong. There is usually a small resistance in the battery, which we label little r. And you can see that little r is in series with big R, because the current goes through big R and then it goes through the battery itself, if you like. And so these two resistors are in series, and we have learnt the formula that when you've got resistors in series, the total resistance in that circuit is the sum of the two. So the total resistance in this circuit is big R plus little r, which means that V is now equal to, by Ohm's law, I into R plus R, because R plus R is now the total resistance in that circuit. And now we introduce a new symbol, the symbol E, but it's a script E, so it's written in this kind of curly form, and that stands for electromotive force. Now, don't be put off by the word force. It actually isn't a force at all, it's a voltage. E is nothing more than the inherent voltage of the battery, but we call it E, the electromotive force. So strictly, the electromotive force is equal to I into R plus R. Now, why do we do that? Why do we assign the letter E to the battery's voltage? It's so that we can distinguish between the inherent voltage of the battery and the voltage that drops across the resistance. Let me explain what I mean. Here is the battery, here is the resistance, capital R, the current flows I, and the internal resistance is R. Now, what is the voltage that drops across this resistance here? We measure it with a voltmeter, we put the voltmeter across the resistance, and we will find that the voltage will equal the current times the resistance. That is the voltage drop across the resistance here. But that V there is not the same as the inherent voltage, the EMF of the battery itself, because there will also now be a voltage drop across the battery because there's a resistance associated with the battery. So there will be a voltage drop across the battery, which we will call the voltage drop across little r, which is the battery, which will be equal to I times little r. And since we know that E is equal to I into R plus R, which is of course equal to IR plus I little r, that means that E is equal to, well, IR is V, which is the voltage drop across the main resistance, plus I little r, which is VR, which is the voltage drop across the battery. So now you've got this peculiar situation that the inherent voltage of the battery, E, the EMF, is principally dropped across the main resistor, but not entirely. A little bit of that EMF will be, as it were, dropped across the battery itself, because the battery itself has an internal resistance. So normally we would have said that the whole of the battery has a potential drop across the resistance. That is no longer the case, because there's another resistance in series, and that resistance happens to be inside the battery. So there are a variety of ways of writing this value of E now. We've got that E is equal to V, the main voltage across the main resistance. I could even put a capital R there to show that that's the voltage drop across the main resistance, plus the voltage drop across the internal resistance. Or you could write that as VR plus, now little VR is capital I little r. That's another way of writing that formula. And you'll need to be able to use all three of these and recognise what they mean in an exam question. Now I'm going to set you a conundrum, or a puzzle. And it looks like this. It's exactly the same circuit as we've had before. The battery, the resistance, capital R, the current I, and the internal resistance in the battery, little r. And now I'm going to give values to these resistors. I'm going to say that, well, let's say that the battery, the EMF, that's E, is 5 volts. The inherent voltage of the battery, 5 volts. The resistance of the battery is 1 ohm, and R, the main resistance, is 9 ohms. Right, so now we know that E is equal to I into R plus R. We developed that before, and that means that I, which we don't yet know, is E divided by R plus R. Well, E, we said, was 5 volts. So that's 5 divided by R plus R. Well, that's 9 plus 1 is 10. So that's nice and easy. That comes to 0.5 amps. So we've got a current of 0.5 amps flowing in the circuit. Now what I'm going to do is to put a voltmeter across this resistance here. So I'm measuring the potential drop across that resistance. And we know that V, that's the potential drop across that resistance, will equal IR. The current flowing through the resistance times the resistance itself. The current is 0.5 volts and the resistance is 9 ohms. So V is equal to 0.5 times 9, which is 4.5 volts. And now you can see calculated for yourself that the potential drop across the resistance, 4.5 volts, is not the same as the inherent voltage of the battery, which is 5 volts, because there is some potential drop across the battery itself. So let's now, I'll redraw the circuit so we can see what we're doing. The battery, the resistance, the current, they're all exactly the same as before, but last time we put the voltmeter across the resistance. This time I'm going to put the voltmeter across the battery, so we can measure the potential drop across the battery. Now you might think, because what I'm about to say is wrong, and I'll explain why so later, you might think that you would say that in these circumstances, the voltage drop across the battery is going to be equal to the current times the resistance, which is now little r, and that's going to be equal to the current, which we know is 0.5 amps, times the resistance, which you may remember I told you was 1 ohm, so it's 0.5 times 1, and that's 0.5 volts. And you might think, hey, that's okay, this is fine. Across the main resistance we had a potential drop of 4.5 volts, and across the battery we've got a potential drop of 0.5 volts. Add the two together, 4.5 plus 0.5 is 5, and that is indeed the voltage of the battery. Hey ho, everything's fine. But actually, you've made a mistake. And this is the reason. I'll just redraw the diagram again. It's just a simple battery, a resistance. And now what we said originally was we put the voltmeter, I won't draw it as such, but we put the voltmeter across those 2 points there. And we measured the voltage drop, and we said that that was 4.5 volts. Then we put the voltmeter across here, and I said that on the face of it you would find that the voltage drop across there would be IR, which would be 0.5 volts. So what I appear to be saying is that if you put the voltmeter across the resistance, you get a voltage drop of 4.5 volts. And if you put the voltmeter across the battery, you'll get a voltage drop of 0.5 volts. But think about it, that cannot be true. Because this is a essentially resistanceless wire. I could put this voltmeter anywhere along here, and it would still record. You know, I could put the resistance, I could put the voltmeter across from here to here. I could put it across there, and I would measure the voltage drop across that resistance. But similarly, instead of putting the voltmeter across here to measure the battery, I could put it across there and there, or there and there, or there and there, or there and there. So when I put the voltmeter across here to measure the PD across R, I will get one value. And if I put it in exactly the same place to measure the potential drop across the battery, apparently I get a different value. If I'm measuring across R, ostensibly I get 4.5 volts, but if I'm measuring across little r, apparently I get 0.5 volts. Well, that cannot be. You can't put a voltmeter across here and get at the same time 2 different readings. That just won't work. Where have I made a mistake? Well, of course, the answer is that when you put the voltmeter across here, you are not simply measuring the voltage drop across the internal resistance of the battery. In other words, it's not just IR. When you put the voltmeter across here, you're also measuring the EMF of the battery. That's the whole point. So what you're actually measuring when you do this is the battery voltage minus the potential drop because the battery has a resistance. So that will be V equals, you'll remember the EMF was 5 volts, minus I times R, which is 0.5, and that gives you 4.5 volts. And that's much more sensible. So, when you put the voltmeter across these 2 points here, you are both measuring the voltage drop across the resistance, which is 4.5 volts, and you're measuring the voltage drop across the battery, which is the combination of the EMF, 5 volts, plus the potential, or rather minus, the potential drop across the battery because the battery has a resistance, which is 0.5 volts, and the net sum of the two is 4.5 volts. So the voltmeter measures 4.5 volts as being both the voltage drop across the resistance and the voltage drop across the battery. So just to make the point, here is exactly the same diagram again. You should now be able to draw this in your sleep. We've got a battery with an internal resistance R, and in the circuit we've got a capital R, but here I'm going to introduce a switch so that I can either open the circuit or close the circuit, and I'm going to measure the voltage across the battery. Now when the switch is open, ordinarily when it's closed there will be a current flowing. When the switch is open, no current will flow. And so the voltage, which we just showed before, is equal to the EMF of the battery minus IR. If no current is flowing because this circuit is open, then in other words it's not a complete circuit, so no current can flow. If I is equal to 0, then V measured on the voltmeter will precisely equal the EMF. So when the circuit is open, no current is flowing, you put a voltmeter across the battery, you will measure 5 volts. You will actually measure the full EMF of the battery because no current is flowing. So there is no potential drop across the battery because there's no I. But if you then close that circuit, then the V you will measure will be E minus IR, and now because you've closed the circuit, a current will flow, there will be a current in the battery, therefore there will be a potential drop across the battery, and therefore the voltage that you measure will be lower than the EMF, and it will be lower by the amount of I, the current, times R, the internal resistance. And finally, how do you measure internal resistance? Well, you use almost the same circuit as before. You've got a battery with an internal resistance R and an EMF E. And this time you have a variable resistor. In other words, a resistance that you can change the value of. And you put an ammeter in the circuit. That ammeter, of course, is going to measure the value of the current, which of course will be determined by the value of the resistance you choose. The higher the resistance, the lower the current. And what you do is you simply change the value of R. Remember, E is fixed, that's the value of the battery. But you change the value of R and you measure the associated current that you get. And you also measure the voltage drop across the resistance. And you plot the voltage across the resistance against the current measured by the ammeter. So for each value of R, as you change the value of R, for each value of R you measure the associated V and the corresponding current measured by the ammeter, and you plot. And what you will get is a series of points for each value of R. You'll get a V and a corresponding I, and you'll find that those are all on a straight line which looks like that. So in other words, as V increases, the current decreases. The more the potential drop is, the smaller the current will be. And that's perfectly reasonable because as the resistance increases, the current, of course, is going to decrease because you're putting more resistance in the circuit, so you're going to get a smaller current. But as the resistance increases, the potential drop across it will increase because the potential drop across it is I times R, so that potential is going to increase. So you're always going to find that as the voltage increases, the current decreases. Now, let's just remind ourselves what the formula is for this circuit here. We know that the total EMF E is going to be the potential drop across the resistance here, plus the potential drop across the actual battery itself. And that is equal to, E is equal to VR plus, VR here is just the current times the internal resistance R. And I just want to rearrange that to say that VR is equal to minus IR plus epsilon. Or rather E, meaning the EMF, it has a sort of epsilon look about it. Now, why did I put it in that form? Well, you should know from your maths class what the formula for a straight line is. The formula for a straight line where you're plotting on the y and the x-axis in this kind of way is that y is equal to mx plus c. I hope you've all done that in your maths class. I can't explain it to you now, but really that's a fairly basic understanding of a straight line, the formula of a straight line, where m is the gradient of the line and c is where the intersection of the line with the y-axis occurs. So y equals mx plus c. But you'll see that on the y-axis we are actually plotting the voltage, and on the x-axis we are plotting the current. So for our purposes, v is essentially y, and x is essentially I. And so if you just inspect these two formula here, you can see that for the purposes of our formula, m is the same as minus r. All right, because the x component for us is I, so m is equal to minus r, and for us c is equal to epsilon, because that's the term at the end of the formulae. And so from our graph you can instantly see how you can measure both R, the internal resistance, and E, the EMF. R is simply going to be the gradient of the slope. Why is it negative? Because the slope is going backwards. If the slope were going that way, then the gradient would be positive. But because the gradient is this way, that's a negative gradient. So essentially, when you measure the gradient, it will come out to a negative number. But the absolute value of the gradient, that is ignoring pluses and minuses, the absolute value will be the value of the internal resistance. So that's the way that you can measure the internal resistance, simply measure the gradient. And for good measure, if you project this line back to the y-axis, the point at which it crosses, which of course will be a voltage, will be equal to the EMF. So if you want to know the EMF of the battery, you just project this back, and at this point you read off on the scale here the full EMF voltage of the battery.